Hi, welcome. This is week 2, session 4. We're going to be looking first of all at a relative humidity recap, following on from the session that we did prior to this one. We're going to have a look at a few examples of wet and dry bulb temperature readings, of which I will give you a list of those readings, and I expect you to complete them and feed them back to me when you're ready to. Okay, without further ado then, let's get that psychrometric chart up and get them cracking. Okay then, so obviously this is now a familiar view to yourselves after the coverage we did in session 3. Just nothing's changed, everything's the same chart. You can see here the dry is still upwards, the wet is down at an angle to the right, from left to right downwards, relative humidity on that curve, and then the dew from right to left. So I'm just going to quickly pull some random percentages out of the air, temperature readings. Let's go with dry, wet. So let's put relative humidity equals question mark, and then we're going to do dp, dew point, equals question mark. So the dry, well, let's say it's 21 degrees. And then wet, let's say wet is, let's say 16.5 degrees. Okay, let's see how we'd have gone with that then. So the first thing we do is we take the dry temperature, first of all, here. Okay, just going to pull up my fantastic ruler, and I'm going to, there's no quick way of doing this, I'm sorry. Right, so our first reading is dry 21 degrees, so we're going to look on the bottom here, and we can see there is 20, 21 is just there, so I'm going to bring my ruler over just there like that, and then draw in black because that's denoting the dry bulb. Okay, there we go, and pull that aside, and now let's put a little bit of an arrow there and label that as 21 degrees. Second reading is the wet bulb at 16.5 degrees. So let's get this to the angle. That's not helpful when it does that, if I was to be brutally honest. That's about there, isn't it? So wet is 16.5, so I'm going to place it there. You can check with me afterwards whether or not this is correct. 16.5, let's move that. As you can see, well, I've not put a line all the way across down to here. There's no point, because all we need really is just this epicenter here where the two lines cross. So really, we just need to go to that point there. Okay, so that represents, as we can see just here, 16.5 degrees. So the next thing we need to do, we can move this over here. We've got our relative humidity, which is in blue, and this is that curve. So we can get rid of the ruler for a second. And let's go in a little bit. Blue. So the relative humidity is crossing at this point here. So we can follow that up freehand as carefully as I can. So it's just under half. Okay, so we can see there then that that's coming in around about 64%. Okay, let's put that there. And I'm reading it from, obviously, this from here. That's obviously 60% there. And then we're a little bit above that, aren't we? So I would say, yeah, about that 64%. So let's line that up so we can get the numbers correct, right? So we can wipe that out there, and now we know that the relative humidity is at 64%. And now we're going to go to our dew point. Okay, so let's get our ruler up, and obviously we're going to draw straight through that cross section again. Everything goes through there. So let's get down to there. Let's scroll in a bit and let's get Let's get down there like that, and we go now. All right, we're going to put our ruler through that point there as best we can. That's about right. And then we're just going to draw straight through there. Okay, and let's just give that a little bit, and we can see if we scroll in that everything's gone through that line, and it crosses just in the middle there. So we've got 10, 11, 12, 13, 13.5. Okay, 13.5. Then let's line that up. So 13.5, let's erase that. There we go. 13.5, change the colour of the pen. 13.5 degrees centigrade. So obviously at the moment then 21 degrees dry and it's 16.5 on the wet. If or when the temperature drops rapidly from 21 degrees down to 13.5, this is equal to maximum condensation, or the point at which water vapor will leave as a gas and return to a liquid. I'm just going to add or a solid, and that's because in some circumstances, some rare circumstances, especially in the polar regions, extreme cold, where you have people where you exhale, you breathe out, and it actually freezes instantly on your lips and on the beard and whatever, and on their eyelids and so on and so forth. So it's possible to just blow hot air out straight into freezing temperature and it'll freeze straight away. So it actually goes from a gas to a solid almost instantly. So that's why I've just added that there. But in general, it'll return to a liquid, e.g. it'll return as a liquid as condensation or dew on the ground, etc., etc. Okay, let's get rid of the rulers. So that's the recap. Hopefully all of that makes sense. Obviously all this writing doesn't make sense now because I've just gone and moved. Well, let's get rid of that. Right, what I'm going to do then, I'm going to get rid of that, is what I'm going to do. And then what I'm going to do, I'm going to give you a list of readings of dry and wet, and I want you to tell me what the dew point and the relative humidity is. Okay, and also there'll be a few trick ones in there where I will give you the dew or the relative humidity or the wet or the dry. You'll have to determine which one is missing. Okay, so let's do that. Okay, so as promised, there are some values for you to work on. We've got the dry, the wet, relative humidity RH, and dP as in dew point. The first two very easy. Just follow the psychrometric chart, follow the directions of the arrows. Does get a little bit harder for the third and fourth, obviously because you've two values left. So for instance on the fourth one you have a percentage of 72.6, a dew point of 20.9, but what are the temperatures for dry and wet? Now what I want you to do, you need to show this on a psychrometric chart, and what I don't want you to do is to just write down the values, because that's very easy. I want to see how you've done it. So please use a psychrometric chart separately for each one. Okay, I have provided a link. You will get access to a psychrometric chart. Just do those on a psychrometric chart I want your name on a psychrometric chart, those four the missing values for each of those four lines there. Okay, so now that's complete, we're going to start looking at heat loss in the next session. We're going to look at ventilation, fabric heat loss, thermal heat loss, and air exchange to heat loss. Okay, so that's coming up next. Okay, so the second part of this session, we're going to look at the principles of heat loss and gains in buildings and how to control. Okay, in your student book, you'll want to look at page 62, where it gives you basic explanation of these things and contributing factors, of which we're going to look at a little bit later on. There's a few calculations in there I'm sure Josh Hobday will be picking up with you just in relation to those. But also on page 64, there's further explanation about the methods of controlling heat loss from buildings. And so what I want to do is to go through the most important parts of the heat loss, because it's important to understand exactly where. I mean, some of these will be surprising for you, but let's see how we go. So in terms of heat loss and heat gain, if we look at the heat loss first, we can see in that image here. Let me just get my highlighter ready. The biggest culprit, through the walls. Okay, through the walls. And obviously with a structure especially, it's not so much a terraced house structure, where a terraced house, I'm sure you all know what terraced house is. Let's just take a quick look. Let me just change my ink color, and let's change that to black. So here we are, typically that's the end gable of a house like that, and then we go along, there's the bridge like that, so on and so forth, and then we'll see several houses together like that. Let's just put a little door in each one. Lovely, lovely, very nice. And let's have a window as well. Look at that, what a house. So we're not so much worried about well, we are worried, obviously. We still got look at this drawing, what a wonderful drawing. Look at this, look at that. Who wouldn't want to live in this house, eh? So we've got our heat loss there in terraced housing, as in the example that I've just so beautifully drew. You can see that obviously only the front of the house here, and then obviously the back side of the house will be actually expelling heat. So it's not necessarily 35% through the walls. Okay, so that's the image you see there is for a single detached house. In other words, a house that's has no adjoining house. What we can have though, we can have two houses. So let's do it this way. Let's get the old eraser on this. Oh, that's yeah, get rid of that. In fact, I might as well just draw on the damn thing again, hadn't I, really? So pen, there we go, go along a little bit further like that, and there we have two houses. Each has a front door with a doorknob there, and at least one window. Look at that, wonderful. My roof does look a bit sad. It should really be about there like that, but the point is, oops, not even there, more like there. The point is it's on three sides now, quite obviously. Let me just get my highlighter. So we're expelling out of there, there and there, and also at the back of the house there. So on three sides. Okay, so getting rid of this, we can see, interestingly, one of the obvious things is 25% through the roof, and that's most of you, and if not all of you, understand that there is a huge amount of onus and lots of published material, often on the news, adverts, so on and so forth, about insulation through the roof, etc., etc. There's lots of schemes where you can get free insulation for people with certain economic problems, or they don't have access to the kind of money that would insulate a roof. But loft insulation or roof insulation currently in building regulations, I believe, is 600 millimeters. Okay, there's your insulation there. So at least 600 mil deep in the attic. Okay, and it makes a vast difference. So that's going to dramatically cut out what's going on there. Another interesting one is actually through the windows and doors, 25%. So again, this is why we stress about double glazing, triple glazing, even. These are fairly obvious. These are fairly obvious where we lose heat. But also we have, what about this one? Through the floor. Did you think about that one? Through the floor. Well, that's conductivity again. Don't forget, heat always moves to the coolest point. So all of this, what you see here, all of that can reverse during hot summers. So if we say that, or let's say, let's change the ink color first. Right, let's say that. So inside, let's say inside is 23 degrees centigrade, and then on the outside, let's say the outside there, it is 31 degrees. So obviously where it's saying heat loss, that now becomes heat gain, because the heat always travels to the coolest point, so it's going to travel into the house. It becomes heat gain. And that's just the conservation of laws, the law of conservation for energy. That's just the way it will work. So that's why they say about shutting your blinds and getting insulation. Certainly things like argon gas within the double glazing between the glass panes to try and block out some of the solar gain from the sun, so on and so forth. But it's seasonal. It's climatic. In other words, it's down to the climate, the weather, internal, external temperatures, and internal, external temperature differences. So they all come into play on that. Okay, let's get rid of that, and we take a look at heat gain. So this we've covered in an earlier session, where we can clearly see there some of the stuff that's happening. Now, one of the things that we didn't mention was obviously the person themselves. This person here, look, sat at the desk there, looking like on a computer. It's generating heat. The person's generating heat through obviously conduction in the first place, with burning fuel, exciting all the molecules within the muscle structures, etc., generating heat as energy. That's being released, and then that's convecting and radiating. Then you've got the machine, the computer, that's doing it. They've just put the kettle on over here, look. There it is. There's the old kettle, look. Whoop, whoop. Right, time for a cup of tea. All of this is bringing in heat. We can see the solar gain coming in there. Also, so we've got low cloud here, so that's stopping the heat from escaping through cloud cover. We've got heat rising up into the attic, so the attic's becoming very, very warm. And don't forget, it's going to be insulated as well, so it'd be absolutely sweltering in that roof. And we've also got the heat balance. We've got this heat balance here, look. And really effective, what it is, this thermal mass. So the ground is expelling heat as well. So there's, as a result of conduction, with the heat in the ground and the thermal mass, that is now releasing the energy in the form of heat in a convective way, in convection. Okay, something we're going to look at in a later session. In fact, it will be session 5, where we start looking at basic U value. Now, I'm not going to go too deep into what U value is at the moment. Effectively, U value is it's a unit, a measurement, a unit of how much energy in watts. Okay, I'll explain what watts are in the next session. Effectively, it's joules. A joules is energy, but when you add movement to energy, it then becomes watts. So it's joules per second. Okay, but I'll explain that in the next session. So you can see here that the top one here, ordinary single glazing. Not many homes have got single glazing now, but you can see the U value here at 6.2 is extremely high. Now, if I was to say, now we've done this in the first session when we did conduction convection radiation. Do you remember what the building regulation requirement was? What was the maximum permissible allowance for watts of energy to pass through a fabric? So from inside to outside, it was, oh, what is that? Oh, we've got the highlighter pen on, that's why. Let's move that a second. Let's change to a pen, and it was 0.33 watts per square meter per degree difference. Okay, so that U value there, what happens with U value is we've got the U value is the reciprocation, so we've got 1 over R, and the R is the total amount of resistance for all of the fabrics that make up the wall. So you could have a plaster coat, then a plasterboard, then a timber stud, then we could have a cavity, then we could have a block wall, external plaster. So we add all those up together, all the different resistance values, and we reciprocate. In other words, we divide 1 by all of those resistance values, and then if it exceeds 0.33 watts per square meter for every square meter, then it doesn't comply to building regulation. So we can see that going back to the highlighter, so you can see when we get standard double glazing there, we can see that this figure here is dramatically reduced from 6.2 to 2.9, dramatic. And then we can add various gases in, so double glazing and argon gas, as I mentioned, has come down another 0.3%. And then we've got double glazing, low E there, and then right the way down with low E, that's low emission by the way, low E and argon. Look at this, right down to 1.61 from 6.2. That's a huge difference. A huge difference. But it's not always so easy just to get the most thermally efficient or resistant materials together to make a wall, because we have a problem with condensation and something called interstitial condensation, which we'll look at in session 7. Okay, so that's something to look out for. But that's what we're looking at. It's generalized heat loss reduction. It's a pretty good example of how that works. Now, something about ventilation that people, when you mention ventilation, people automatically think, oh, well, that's an air conditioner, or that's a fan or an extractor and such. But what you're looking at there, that's natural ventilation. Natural ventilation. It comes in from everywhere. And to give the accidental ventilation its proper name, we'll call it a draft. That's right, you know, it's drafty in here. There's a draft coming through the door, so on and so forth. Wherever there's cracks and crannies and nooks and crevices and so on and so forth, there will be drafts. Because if we seal a building so it's airtight, what we call hermetically sealed, we'd all suffocate to death because no oxygen would get in. Okay, so that's pretty obvious. So we need to control the ventilation. And when we look at the amount of heat loss in a building, where we say, oh, it's 35% for walls, it's 25% for roof, 25% for windows and doors, and so on and so forth, 15% is drafts. You could, you know, and a well-built home still has drafts because we have that thing called stack effect. And if you remember, I mentioned that in the first session that we did, where we have there's our structure, a fine structure it is too, and then we have the let's say highlighter. Let's use that one. I'm going to just get in my pen ready. highlighter in colour. Let's go for, so we've got blue coming at the bottom, so we've got blue coming in there. Okay, this is the natural stack effect, in other words the balance. Do you remember what I was talking about there, where the air is brought in through natural crevices? So it could be air vents, it could be chimney stack that always acts as like a vacuum. It's like sucking air through at the bottom until we get to up here where all the air effectively is through convection, so on and so forth, is heated up and expelled, and we lose it through the roof and through various ventilation and so on and so forth. So this is stack effect, and now the point to what I need to highlight here, I'm going to use a green, is that here, okay, in the middle of the building, in the very middle of the building, that should be 0. Okay, that should be 0. So it all works on pressure. So this is all, shall we say, pressure in, pressure out. And we need to get a fine balance here. So if we're getting too much cold pressure coming in, that's going to have to push the warm air out a lot quicker. So the building's going to cool rapidly. It's going to be not the best in terms of human comfort. Whereas if we don't have too much cold air coming in, as the hot air goes out, it creates like a vacuum. It'll suck it through. What we don't want to have, we don't want our pressure at this point here, our balance there. Let's say that was 0 there and 0 there. We've just shifted this line upwards. We've just gone up to there, to there. So what we've got now is that generally the building is out of balance, and then we're going to have majority of this part of the building is going to be cool, and then your attic's going to be lovely and warm. So you can either move into your attic with a sleeping bag, or you can just get this right and make sure that the building is has a proper stack effect. There is procedures in place for that, where you get energy certificates. All buildings, new buildings, need to be tested for compliance for the leak, air leaks, etc., to conform to get a performance certificate issued. Something we can look at later on request. The next thing we look at exhaust. So with exhaust, what we mean is ventilation, extraction, so on and so forth, and we need to understand where we actually see them. So we see them here. So if you've got a roof, a standard roof, and you look up and you look under what's called the eaves of the roof and the soffit, you'll see ventilation, little slots, or you should see slots there. Older buildings not necessarily so, but certain new builds, you will see vents all the way along underneath the sides of your roof, and then you'll see there's also vent in the top of the roof there. And also, like in my house, let me just change the pen colour, we see vent tiles on the actual, so in every now and then roof tiles are actually ventilation tiles. They're still part of the roof system, but it all creates a ventilation, it's an exhaust system. Okay, here's a good one. This is a vent brick, an air brick, and I actually went to do a survey in Northampton about a week ago, and the friend of mine who was buying a house had a real concern about huge condensation in the cellar, and this property had a cellar. Not all properties have cellars, and they said that they were worried, and would I come down and do a survey, what we call dilapidation survey, effectively, and to have a look at the issues, what might be going on there. When I got there, it wasn't such a problem. The problem is first of all, there was only one air vent. On the front of the house, it was a terraced house, so you had adjoining houses, and it was on a steep hill, and this house was near the bottom of the hill. And Severn Trent Water actually said that the reason why the cellar was so wet was the house next door has got a leak. But I said, well, that can't be so, because obviously water is always going to travel downhill. So unless unless the water leak is just pouring through constantly like a small stream, then obviously that's not going to be the case. And when I did actually go and survey it, most of the condensation was at the top of the walls, underneath the underside of the ground floor joists. So what that indicated when I first got there, there wasn't an air brick at the front of the house, and neither was the one at the back. Oh, sorry, there was one at the back, but it looked like this. Now, I've just mentioned this in a previous session, where previous occupants of the building have decided to change the look of the external grounds of the house, etc. And as you can see, they've the last person in this house, they've decided to put stone down on top of maybe a tarmac drive or slabs or whatever to make it look really nice. And the problem is that they've risen, the finished ground level has risen, which means now the potential for damp to penetrate through the brick is greatly accentuated, and of course the air brick now is starting to get covered up. So there's going to be serious condensation issues there, rising damp certainly, leading to lots of human comfort conditions in respiratory terms and so on and so forth. But we can look again at that later on. Most modern houses have double glazing, and most double glazing have trickle vents, and the trickle vents on windows, etc., are simply these here. You can see not the best highlight pen there. I think we can just let me just change that into a pen that we can see. Change the color. Here we go. Let me just highlight that there, and there. So there's vents at the top there, so in each room. Okay, at the bottom, if you look on the inside of your house, you should see two little tiny slots down the bottom. They are not ventilation, they are not trickle vents, they're what we call weep holes. So if condensation does occur on the inside of the room, on the inside of the window, the condensation can roll down into the weep vents and then outside onto the sill and away, not causing a problem, but that would be rare. In the olden days, if any of you have not got double glazing, or you don't have, I mean, there is a lot of double glazing about that doesn't have trickle vents. In fact, the house I surveyed last week it had double glazing, but it didn't have trickle vents. So you'll often see something like this, which are wall vents, and usually the wall vents, they are up towards the ceiling in each house, and they're part of the building regulations. You've got to have ventilation within each of the rooms, especially the living room or wherever there's a gas fire because of the carbon monoxide emissions, etc. So you can't just, so many people when they decorate, they just plasterboard over it or plaster over, they cover it up, and then they don't have ventilation, and then all sorts of problems are going to arise from that, from a human comfort side of things. Moving on to thermal bridging, let me just put that down there. Thermal bridging. Now with thermal bridging, this is the thing that people take their eye off the ball on this, because this is all about conductivity. Conductivity, there we go again, here it is, conductivity, convection, radiation. It's one of those things in physics that obviously it's never going to go away. Heat will always travel to the cooler point. So what we're seeing here, let me get my highlighter, and okay, so here we can see a typical construction. So on the outside here, let's supposing, so we've got a external brick wall from the exterior, and here we've got a brick tie, this metal brick tie, which is usually in the shape of figure 8 like that, usually, but this is a different type of system. Effectively what you would have in the old style bricks is that you would lay a brick like that, let's put the holes in like that, and then you would lay a block on the internal like that, and then you would put mortar over the, let's try a different color there, let's use green. So mortar is applied onto each block and the brick, and then another brick and block is so in other words, that this here is trapped in between the two, tying the wall together. So that's what the brick tie does. This is pretty much the same principle, but you can see that it's connected here. It's gone through, straight through, and fixed into a steel stud on the inside. Okay, now the problem we've got with this, and a big problem that we don't, that they haven't really thought about, or at least we can't really see whether what contingency plans they've got for this, but heat. So if we say the inside heat here, let's say it's 22 degrees here, and on the outside it's 13 degrees outside, heat will obviously penetrate the steel stud, and then that heat is going to travel along this steel tie all the way through, and you remember about equilibrium, it only stops when it is equal. So all of this brick, all of this tie here through conductivity is being heated up, and as a result thermal bridging has happened. So all the heat is travelling out from the inside out through the brick ties through to the brickwork itself. Now it's not going to warm the brick up too much, and I wouldn't imagine it's going to do that, but what it will do is it'll ensure that there is a steady and consistent flow of heat energy flowing from inside to outside, and you really don't want that. And the strange thing is they've got all this insulation here, they've got a vapor barrier here, and they've got all this insulation here, so on and so forth. They've got neoprene washer just here, which is that's an actual, and that's a bridging in itself. You've got sheathing here, another form of insulation, insulation here, and yet you've got this issue here with thermal bridging. You see it in double glazed windows with packers. When people are fitting windows, sometimes the thermal bridging is touching the brickwork and so on and so forth. So it's a bit of a nightmare, but there are ways around it. Where if we take a look at, let me get rid of my, okay, let's get rid of that there, and we can see here this is a rigid insulation form system where you can see that there's various layers of insulation. There's a hard wall internal system here. So this here is panels that's fitted into, used to be called a gyprock system, but I dare say there's lots of other different names for it now, or Lafarge gyprock, or metal stud partitioning, where there'd be various, the way it's connected between, let's just change my pen again to, so where the connections are made here, usually there's insulated connectors as well, so that the heat it's not a thermal bridge whatsoever. So it's a well thought out system where even the brick ties that they're fixed through to the rigid insulation system. Remember the brick ties up here. So when if heat does travel along the brick tie, it's going to stop at the insulation there. It's not going to pass through. A very rigid system in terms of thermal bridging, but likewise it could be costly as well, could be expensive. Now nearly finished. We've got air changes per hour. These are governed by building regulations. Okay, and effectively what they mean is that for every cubic meter in a building, in a certain part of the building, like a canteen, a commercial kitchen, a factory or a workshop or a garage, so to speak, depending on the type of use for the building, will depend on how many air changes per hour. So you can see here a bakery, obviously we're talking very hot temperatures, lots of humidity, It means that so if we had 300 cubic meters within the bakery, then that needs to be changed 20 to 30 times an hour. So every 2 minutes, at least every 2 minutes, it's going to have to be changed. Every single bit of air in there. So there's a lot of extraction and ventilation involved with that. What I want you to do with this, I want you to investigate this a little bit further, because this is going to be exam stuff you must know. Okay, you're going to have to understand, well, first of all, where you get these regulations from and how you apply them to various examples. So, for instance, what part of the current UK building regulations cover ventilation? So you got part A, B, C, so on and so forth. Which part covers ventilation? You need to tell me what part of them. And when you found them, you need to look into them and investigate the following. So what are the required air change rates according to the building regulations for the following? So I want you to tell me how many air changes per hour for a domestic living room, as in your living room in your house. It's quite easy. All you need to do is to measure the cubic meterage. Whoa, don't know what happened there. That's because I didn't have my pen on. Right. So let's change the color of this and I'll show you what I want you to do. So if we look at the outlay of your living room, a floor, let's say it's square. So we've got length, and then we've got width, and then you will have height. So to get cubic meter, you would have length times width, which is equal to meters squared, because you're only measuring two things, length and width. But when you get in cubic meters, you will measure length times width times height, and that is cubic meters. Look, the 3. That's because there's 3. 1, 2, 3. So cubic meters. So measure the length of your living room and the width. Measure the height. It'll probably be 2.4 meters. It usually is. And then look at the building regulations and tell me how many air changes should your living room have per hour. You need to do the same for a classroom. So the classroom that you're in, so it could be C204, C205, C206. You just measure the class. You can. That's easy for you to do. In fact, you don't need a tape measure, because if you look up at the ceiling in any of the classrooms, you'll see what we call a tile and grid ceiling just above your heads. And each of these tiles are 0.6 meters, or 600 mil square. Okay, so just count the tiles, and then if there's 10 tiles, then it's 6 meters. You can be fairly rough on that. That's not a problem. Library, we have a library downstairs on the second floor, so you can go in there as well. So according to building regulations, what part of the regs cover it, and tell me what the air changes per hour are for the living room, the classroom, and the library. And the last thing I want to do is to look at air change and a sustainable solution. So while according to the building regs we have to change the air, because obviously of human comfort, so it might be getting too humid, we might be getting too much moisture in there, which has gone above 70%. Now we're getting really clammy, claggy, sweaty, we're perspiring, we're getting dehydrated, so on and so forth. So we're all about the stale air, we're about the germs and bacteria that we're all breathing out, and it's all mingling, and someone's got a nasty cold and now we're all catching it, so on and so forth. So let's say that a classroom, and this is an absolute random number, because I don't want you to think the number I'm about to give you now is the answer to the previous question for classroom. It's not. Let's just pick a number and say 20, which is ridiculous because I know it's not 20, but let's say that a classroom needs changing 20 times an hour. That's a lot of heat energy that's passing out. Because if we look at this, what we're looking at here is what we call a thermal wheel. It's an exchange wheel, heat exchange wheel. Now there's lots of heat exchange systems, certainly more towards building services pathway. You would have a deeper connection to that, because a lot of you will be designing with these systems, and you'll be au fait with them. You'll know what they are. So what we can see here then, let's just change the ink color one more time. So we can see the fresh air here is coming in to the wheel. Okay, fresh air is coming in, and it's coming in at 74. So this is coming out from outside. So we've got 32 degrees and 74% humid. Now ordinarily that wouldn't be very nice. You don't want your classroom at 32 degrees and 74% relative humidity. What happens as it comes through the wheel regulates the temperature. Okay, so it as you can see, it's only allowing 25.6 degrees in and 66% relative humidity. Now the 66% relative humidity is fine, that's well within the comfort range. The temperature is a little bit higher, but because the air is being forced through, it's being vented into the room at speed, that's automatically cooling the air down. Okay, so it's cooling it down. As we can see, we come round to here, 23 degrees. So the classroom, our classrooms are generally set at 21 degrees. So there may be some mechanical ventilation in place, so we may have air conditioning that's supplementary to this thermal wheel, and that it's at 55% relative humidity and 23 degrees. And then as the wheel keeps on rotating, out it comes again like that, and we can see that the air that circulated in through to the classroom was heated up again to 29.2 and 73% relative humidity, which is uncomfortable again. So that will happen 20 times in an hour. So what we're doing here is as the energy comes in, we're heating, we're cooling it down to the point where it's comfortable for us. But in a cruder form, when we vent hot air out of the classroom, let's suppose we're venting out 25 degrees and we're bringing in fresh air at say 15 degrees, perhaps we're bringing it from outside itself. Well, what the thermal wheel does, or the heat exchanger does, it traps some of the energy in the return air, bottom right corner, return air. It traps some of the energy from here in the wheel, so that when it draws the fresh air in, top left corner here, when it draws the air in from here, there's enough energy inside the wheel itself to heat. Let's suppose it's 15 degrees that comes in from fresh air, and by the time it comes in the supply air, it's heated up to say 19 degrees. So 4 degrees has been captured from the return air in the form of energy as it goes out as an exhaust air, and then as we pull fresh air in, what went out with the return air, 3 or 4 degrees has been kept in the heat exchanger, which then heats up the fresh air as it comes in, so there's less air to actually heat up, so we don't have to use the energy for those 3 or 4 degrees. It's a very clever it's a very clever invention, far more sophisticated than these drawings are, but there you go. That'll give you a bit of an idea, a bit of a heads up about the principles of heat exchange. So that's where we finish. What I want you to do then is to take a look at the questions that I've given you. Okay, I want you to do the 4 psychrometric ones on the psychrometric charts themselves, and I want you to answer the questions about the building regulation. On the next session, we're going to look at conductivity, ventilation and heat loss. We'll have a recap and we'll look at a few more things to do with that, and then we're going to start off with basic U value, where we'll start ending up doing basic calculation with that, of which Josh Hodday will take you through to merit level on that. And just to say, I think you know what I'm going to say, answer the question, give the question back.